qualche esempio sarà chiarito meglio. Ok. Questa è la seconda parte della lezione di 27 ottobre e cerchiamo di vedere un po' di esempi con la classificazione di punti di equilibrio per sistemi 2x2. Therefore, we shall speak English, and our goal shall be to consider different cases of eigenvalues. Our starting point shall be a 2x2 system with coefficients given by a matrix A. At the beginning, to understand how we can reduce the solution of 3 to 4 and how we can build a picture for 4. Okay. But first of all, before cleaning your questions for the moment, if you have some questions connected with this part of the blackboard, we can stop for the moment. Probably to turn to some examples. We shall take 2x2 matrix. Let's start with a concrete example. As I promised, this shall be put in our this classification shall be a separated file in the home page of our course, my home page. And let's first clean the blackboard. Start with concrete example. Example. I prefer to leave only these 2 points together with this part that reminds you, if you have 2 different eigenvalues, diagonal. If we have double eigenvalue, we may have Jordan block, and this means that we have now our first example. That is in terms of equation 3, and our purpose shall build the picture in zeta. So, as we start with example. One, that is following system. Y1 prime shall be minus 1 plus y2, and y2 prime shall be 5y1 plus 3y2. So this is our system of this form. Our matrix A is, I simply take the coefficients in front of y1, y2, and put in the table of the matrix. So we have first this -1, that is coefficient in front of y1, and then we have 1 coefficient in front of y2, and then we have 5, 3. Our matrix. Remember, we built how we find eigenvalues. We have to find characteristic equation. Therefore, we take A, minus lambda times identity matrix, compute this, minus 1 minus lambda. Then we have 1, 5, 3 minus lambda. As you can see, when you take A minus lambda E, minus lambda shall be minus lambda on the now, because this is identity matrix, while the other two guys are the same as in the beginning. So what we have to compute, determinant of this matrix equals 0. This is so characteristic equation. So this determinant equals 0 is characteristic equation. And we can solve it. Let us try to solve it. This by this minus this by this. This is the determinant. So we have minus 1 minus lambda times 3 minus lambda. Product of the diagonals minus the product of anti-diagonal minus 5 equals 0. This is our characteristic equation. As you know, any equation of order 2 may have two real eigenvalues when discriminant is positive, one double eigenvalue when the discriminant is negative, or has no real values, roots, when the discriminant is negative. In this case, we shall see that roots are complex. Our case is lucky. Here we should have real values. So we have, I can write this as lambda plus 1 times lambda minus 3. I change signs in both factors, so this will not change finally the sign, and minus 5 equals 0. Let us open the brackets. So we have, from here we get lambda square, minus 3, 1 is minus 2 lambda. Then we have 1 by minus 3 is minus 3, minus 5, minus 8, equal 0. Which are the solutions of this equation? Let us see if you can find them. Can you propose me some solution? One root. Typically, in all my examples, I'm trying to find integer roots. What do you think? What shall be the root of this equation, one of the roots? Let's see if you have some proposal via chat, or if you... Yes, Martina already answered, minus 2 and 4. So we have lambda 1 is minus 2, lambda 2 is 4. Very good. So what we can say? We have two eigenvalues and with opposite sign. One is positive, one is negative. Now we can find our diagonal matrix. Here is minus 2, here is 4. So let us write directly our equation, this for zeta. Zeta 1 prime is minus 2 zeta 1. This is due to the fact that D is diagonal, and zeta 2 prime is 4 zeta 2. These two equations are very simple to be solved. So, how we shall solve the first one? For the first one, we have already solution. Zeta 1 of t is a to the power minus 2t multiplied by our initial data, here we shall specify, let us write Z1, 0 is Z1 with index 0, and Z2 of 0 will be Z2 with this small index 0. So we have Z1, 0. This is our explicit solution. And for the other Z2, we can have our solution Z2t shall be this time a to the power 4t. A to the power 4 Z2, 0. So this can build the picture very simply. Let us make the picture for zeta. What kind of relation we can find? For example, how we can, for example, find the equation satisfied by Z1 and Z2 in order to make the picture. Finally, we are interested in Z1, Z2. Of course, if I start with 0, if these two guys are 0, I always have Z1, Z2, 0. Therefore, this point, if initial data there, I have to stay there, cannot go out. But let us assume our initial data, for example, are here. What does it mean? Z1, 0 is positive. And Z2, 0 is 0. What you can say about Z2? If Z2, 0 is 0, this is always 0. So our solution has to stay on X Z1. Always, if Z2, 0 is 0. But what will happen with Z1? When T increases, what happens with Z1? Is increasing or decreasing? I take Z1, 0. Let us take a little bit to have. This is 1, 0. And the second coordinate is 0. What you can say about the behavior of Z1? It is moving on the left or on the right. If I start from this point, we have to move where? Look at our solution and tell me where is the solution. Left or right? Because I shall put arrow, and it is important to put the arrow. If I start from this, Z1 is increasing or decreasing? Look at this expression. Here we have the arrow shall be in which side? Left or right? Increasing, exactly. Therefore, starting from here, you shall see if this is kind of disease, we see that we are approaching the stationary point, and this is not dangerous for our model. Therefore, we will not increase the people infected by the virus. So here we have the picture. If I start from here, you can see that again, if T is negative, one moment, careful, careful, careful. If Z1, 0 is negative, and if T goes to some positive, to plus infinity, this will go to 0. Therefore, our behavior shall be exactly this one. If this is negative, the behavior of our function changes. In t, it is increasing now because we changed the sign. So, similar thing you can say if you start from here, for example. Here you have similar behavior, only careful. What will happen if we hit this point, that is 0, zeta2, 0. Zeta2, 0 is positive. Now we exchange, this is 0, but this is positive. In time, this is increasing. So what will happen? When t increases, our function will go this direction. So is starting to increase, and this is dangerous direction. Similar thing will happen if we start here. We have here, if this is negative, this becomes more negative, decreasing function, and the arrow is here. Finally, we have to build our picture starting, for example, here. And here I would propose you to, I will remind you, the very simple. We said that due to the Cauchy Theorem, our curves, they have to be close to each other. For example, if I take my curve here, my point here, whatever will happen, this will be close to this because I'm very close. This is the first principle, that the curves are very close. And the next principle, due to Cauchy, they never intersect. You cannot intersect two curves if you want to build the picture. Therefore, if you see, for example, here, if I have both guys, what you can say, this is decreasing and zeta2 is increasing. Therefore, I have to build the following thing. This is a curve such that zeta1 is decreasing, zeta2 is increasing. And now it is quite easy to put my arrows. I know that when I am close to this, the direction of the arrows shall be the same. Therefore, here I have very nice picture, and the arrows are like this. I have a choice. Similar thing will happen here. For example, my arrows shall be very close. Therefore, I have to put like this. I don't care more to see explicit solution. The important thing is to recognize this is important, and we can say that 0, in this case, 0, is attractive point for this x zeta1. 0 attracts zeta1. So we attract the behavior, and in this direction we have very nice behavior. But in direction of zeta2, we have instability. 0 is unstable. Unstable, this is very important for application. This means this is direction in which, for example, everything can become exponentially increasing. Unstable on zeta2. Why it is unstable? Because our solutions, they instead of approach, they go far away from our stationary point. And then we build all curves. For example, if I want, for a moment, I shall clean now this. And we can build here the curve. Again, you can say, if you start from here, zeta1 shall be decreasing. So we have in this direction, while zeta2 is increasing, is decreasing because this is negative. Therefore, we have such a curve. And then the arrows they're subordinate to the arrows of our axis. And again, if you put here the curves, you have to put arrows like this. So this is an important case when lambda 1 is negative, lambda 2 is positive. This in general happens. It's not connected with the fact here we have -2. Now I shall explain reply to Asia. Only want to finish here the picture. When you have lambda 1 negative, lambda 2 positive, therefore two eigenvalues with opposite sign, this point 0 is the saddle point. Saddle point. And concerning the saddle point, in italiano, sella. So our first appointment is with sella, with saddle point. This means y eigenvalue negative, 1 is positive. Now, why we use instability, the word instability? What is the meaning of instability? And what is the meaning of stability? When we use stability, what we have? A point, and we have a curve of our solution starting from one point. If the curve is approaching our stationary point, we should say stability of our solution, stability of our trajectory. In this case, trajectory is on the axis zeta1, and therefore we have stability in this direction because the curve is approaching our point. If you have a stationary point, you start from a point, and instead of approaching, you start to go on larger and larger distance. If you escape from the domain close to the point, if you go far away from the point, then we call this curve or this trajectory unstable, because you do not approach the stationary point, but you go far away. So if you go far away, unstable. If you approach, is stable. This is the meaning of this stability, instability. And we shall use after this in our next classification scheme. But here I want to understand if this answer is clear or you need a little bit more.
Yes, now I get. Thank you.
Okay, please to stop me any moment. Okay, so you have now the picture of saddle point. Let us go to another case. This is example 1. And we can say that whenever you have eigenvalues, two real eigenvalues with opposite sign, you have saddle point. Let us go now to another example. Of course, here we could go further computing eigenvectors of our matrix, but as I told you, I shall simplify the study. Eigenvectors means if you go from the picture for zeta to the picture for ipsilon, you have somehow, instead of this orthogonal coordinate system, to use two eigenvectors to build in ipsilon your picture. So you have a little bit smashed to a little bit to deform your picture, but essentially the picture is the same. That's why I am asking, what is the picture for zeta? Okay. Now I found that we are really lucky, because at this time I remember that the sun last week came in the midfield, and we couldn't make the lectures very easy. Now, due to the shift of the time, we are lucky and we can continue to work without disturbed by the sun. Okay, next case. Let us take the next case. It is clear that once you find eigenvalues, essentially you can work with the system in Z. That's why in the next example I shall write you directly the system in Z, and we shall try to look the system in Z. So first case in Z was negative. Let us now go further. Of course, in next exercises, we should have the matrix A, which is not diagonal, but in the next example, we shall take directly diagonal and consider example 2. This is example 2. Let us take Z1 prime equal to Z1, Z2 prime equal 4Z2. Now, in the next example, we have two real eigenvalues, but positive. Both are positive. Then you can write directly your Z1t is a to the power 2t, Z1 0, and Z2t is a to the power 4, Z2 0. And let us try to build the picture with arrows. In this case, we have both eigenvalues positive. Again, if you have Z2 0, so if we start from here, what will happen? This is increasing function. So now the arrows are in this direction because Z1 is increasing. If we start from here, for example, again, whenever you start from here, you go in this direction. In any case, remember that if you start from the origin, since this and this are 0, for any time you stay there. But once you take, for example, Z1 positive, your solution is unstable, and instead of approaching, is going far away from you have instability phenomena. The same thing happens here. You can see this. Situation is similar. Z2, you have again instability phenomena. So your pictures are similar, and arrows shall be very, very unstable. And now let us see what will happen if we start from this point. Of course, both guys are increasing, therefore we shall have like this. Something that when you start from here, you shall have such that when t goes to minus infinity, you shall be close to the, because t go to minus infinity, both guys go to 0. Therefore, if we say what is the path of our curves, they are closer and to these points. But they're like this. Let us try to make the arrows. And the arrows are clear because when this is close to this, we have to build arrows very close. Remember that I try to build the curves such that they do not intersect. This is forbidden due to Cauchy Theorem. And similar thing will happen now all other curves. So, and here we have similar behavior. You see, all curves, they escape from our stationary point. They go far away. And this is typical situation when we have lambda 1 positive, lambda 2 positive. We have nodo in Italiano, in inglese not. And here we can say that this is unstable. Instability property is practically seen by the arrows, seen by si vedono delle frecce. Therefore, we have the case of unstable knot when lambda 1 and lambda 2 are positive. We have lambda 1 is negative and lambda 2 is negative. If both eigenvalues are negative, then we have to invert. Instead of increasing function, this shall be with sign minus, decreasing, and therefore our picture we can build without solving the equation. We simply put table situation and then we build the same curves as before. But now the situation is opposite. Instead of escaping our curves when negative eigenvalues, our curves approach. But they never touch this point because remember, this point stationary point. So if the solution starts from this point, remains always there. But with other curves, we approach this stationary point, and there we have stable nodo stabile. We have one unstable and one stable node, depending on the signs of our eigenvalues. This, of course, describes the principal cases when you have two eigenvalues, real eigenvalues. Of course, you can ask me what will happen if lambda 1 is 0, lambda 2 is negative, but this can be seen directly from our explicit solution. If you have explicit solution, so you can build the pictures very easily. Essentially, what I insist to understand that when you have two real eigenvalues, you can have the cases or saddle point when the signs and values are opposite, or you have knots that may be stable or unstable depending on the signs of your eigenvalues. This, I think, we can complete our example and pass to the next example, which is very, very important, the case of complex eigenvalues. And this is exactly the case of oscillators, models connected to neuroscience with Kuramoto. And that's why it was important to introduce at least some basic notions of complex functions, because now we are ready to treat also this case. So let us go to the next example, that is example 3. As I told you, we didn't treat Jordan. Jordan is very similar to this case the last week. So in examples, we can treat also this case. But the essential thing is if you can understand the diagonal matrix, then we have also possibility consider all cases, because we can find explicit solutions. Of course, we need some practice and some experience, but I shall not ask too much from you if you can recognize the type of the stationary point and build a picture in Z. For me, this is the maximum. I shall not insist to make you pure mathematicians, but only guys with interdisciplinary preparation that can also collaborate with mathematicians. Okay, our next example is we start with epsilon 1 prime is equal epsilon 2, and epsilon 2 prime is epsilon 1. So this is a typical case of if you take epsilon 1 sine of t, the derivative of take epsilon 1 cosine of t, the derivative of cosine is minus sine. If you take sine derivative, this is cosine. But sine and cosine, these are, as we have seen, something closely connected with oscillations. So this is typical example. And let us try to see what is our matrix A. Our matrix is 0, minus 1, and here we have 1, 0. We have to find the characteristic equation. So we start with A minus lambda I. In our case, this is minus lambda minus 1, 1, made a mistake, minus lambda. So I subtract on the diagonal lambda, as we already have seen, and then we have to take determinant. Determinant of this guy equals 0. And we know that the determinant of 2 by 2 matrix is this by this minus this by this. So we have minus lambda by minus lambda square minus 1 by minus 1 is plus 1 equals 0. As you can immediately see, you have no real roots, but you have lambda 1 is e, and lambda 2 is minus I. So you have two complex roots. Remember that I squared is minus 1, plus 1, this is one solution. If you take the complex conjugate of phi, this is minus I. This is again a solution, because if you take bar in this equation, and if you know that lambda is complex, you have bar lambda squared plus 1 equal 0, if this equation is satisfied. So if you have I solution, you find immediately root minus I. So on diagonal, you have I. How to proceed? Of course, now we have a problem to present our solution, because formally our solution can be obtained in the following way. Let us do epsilon1t, epsilon2t, that are real numbers, and we take and call this zeta t. So if we interpret epsilon1 as the real part and epsilon2 as complex, imaginary part of a complex function, let us compute zeta prime. Zeta prime of t. We said this is derivative of epsilon1 plus I is a constant, so we do not touch I, plus I, epsilon2 prime. Now we can use our system, epsilon1 prime, this is minus epsilon2. Here I applied my equation, first equation, then you have I, epsilon2 prime is epsilon1. Oh, this is very nice expression, because I can put I in front, and what we have inside is epsilon1 plus epsilon2. Here we freely use complex numbers, and remember that epsilon1 plus epsilon2 is my zeta. So what is our equation? From this equation, we get immediately zeta prime is equal I zeta. How we can solve this equation? This equation we have the possibility to solve because we can interpret this factor exactly as the case of real number. So from here, you put zeta t is a to the power e t. This is very well defined number times your initial data zeta 0. And now we are ready to build the picture, because our zeta already is known. It is defined with this relation. And what is epsilon1? A real part of zeta. What is epsilon2? Imaginary part of zeta. We shall compute after a while, taking zeta 0 equal epsilon1 0 plus e epsilon2 0. Actually, I shall put this like c1 plus e c2. These are real numbers. I shall use this c1, c2 and shall compute zeta. But before going further, stop for a moment and ask you, because here we return back to the use of complex numbers. Why? Because we need solution of this equation when we have initial data given by C1, C2. Here we put epsilon1 0 equal C1, epsilon2 0 equal C2. And we want to solve it. With the help of complex numbers, we arrive at this expression. This is our solution, and after a while we shall see epsilon1 and epsilon2. But before going further, let us concentrate on this line, because this is very important, this equation. I justified on this line this equation, because after this we solve this equation. Let us see if you have kind of observation or something unclear.
Excuse me, I didn't get the derivation of dead. No.
Which one?
Where at the
Here.
right. Yeah, the derivation. Y prime 1 plus E.
Ah, here. Okay, here.
Yeah.
Yes. So we have defined zeta in this way. This is our definition. This is our setting. We say, let this zeta be defined, our definition. When you have complex function with real part and imaginary part functions, you have to compute derivative of this function. How? Derivative of this plus I, derivative of this. And for derivatives, you use this system 1. So, compute zeta prime, y1 prime plus y2 prime. Now, here and here, I use the equation. And here, I use equation system 1. And then, putting I in front, I get something very simple and important.
Okay, thank you.
Okay, well, you're welcome. Now, let us compute the real and imaginary part, and we complete our lecture. Actually, I shall write the answer, and I would suggest you to stop because in any case, today is heavy day. For you, for mathematics, we put too many arguments. Let me go for a real part. We have a to the power et, zeta0 was c1 plus e2. This is zeta t. I use representation with cosine and sine. So this is cosine t plus e sine of t multiplied by c1 plus e c2. I substitute with our definition. A to the power at is cosine and sine. From this, I think this example we shall finish tomorrow. And we shall find, for example, one simple thing to simplify everything. Let us put C2 equals 0, C1 equal 1. What we shall get? We shall get, in this case, this is 1. Zeta t, for this case, is cos t plus e sine t. So we can say that y1 was the real part, so this is cos t, and y2 is sine t. You can say immediately when t is moving, where is your y1 and y2? You see, cosine square plus sine square gives you always 1. So this is circle with radius 1. This is because we started at this point. We shall see tomorrow that actually always here you have circles. And this picture shall be justified tomorrow, is called fuoco or focus. The case when you have kind of circles around your point. And this is the case of colors. But this part we shall finish tomorrow. So I suggest to stop immediately because we worked very hardly today, and start tomorrow with first derivation, more precise with any C1, C2, and see that practically we shall have fuoco. This shall be done without high velocity tomorrow. And for this now I shall stop the registration, and we should eventually leave some questions for tomorrow.